Hello, everyone. Welcome to Percona Live. I'm Dipti, and with me is Tim, and we're here to talk about Presto. Here to give you an introduction to Presto, the SQL engine for the data platform teams for both interactive as well as batch workloads. And I'm Dipti Borkar. I heart Presto. I'm the chair of the Presto Foundation outreach team, as well as the co-founder and chief product officer at Ahana.
Hi, thanks, Dipti, and I'm Tim Meehan. I'm a software engineer at Facebook, working on Presto, and I'm also the chair of the TSC within the Presto Foundation.
Let's get started. Let's start off with an intro to Presto, that's also known as Presto DB. So Presto came out of Facebook, was created at Facebook in 2019. Facebook decided to donate it to the Linux Foundation, and Presto Foundation was created along with Facebook, Uber, Twitter, and Alibaba. There were a couple of business needs that really have driven the adoption of Presto. The first one is just being companies becoming more data-driven. As more decisions are taken based on data, businesses iterate over more data. There's more insights that are needed to run, to create new products, to advance new products, to run reports. All of this has assisted with the adoption of Presto. In addition, there has also been a disaggregation of storage and compute. And as the adoption of cloud data lakes has increased, has also led to an increase in the adoption of Presto. So what is Presto? Presto is a disaggregated, distributed query engine. It's a SQL query engine, and it's ANSI-SQL compliant. It's built to run on both data lakes. Initially, it was built to replace Hive, and the data lake was HDFS. Increasingly, it's AWS S3, GCP, and others. And it was designed to be interactive. It was designed for fast queries on a large amount of data, as well as across different data sources. And I'll talk a little bit about this. At Facebook and Uber, Presto runs at massive scale and can analyze petabytes of data. Now, Presto is open source, it's a very popular open source query engine hosted under the Linux Foundation, as I was mentioning. So here's an architecture of Presto. Presto is a distributed system, and so you have a coordinator as well as workers. Up until now, there was a single coordinator, which was responsible for the query planning, query scheduling, etc. And the workers performed the work on across different sets of data, different partitions, different splits, etc., all in memory. Now there is a new advancement where multiple coordinators are being introduced into Presto as well, and Tim will talk about it later in the presentation. Now, Presto can be accessed using the standard JDBC or DBC protocol, given that it's SQL, and you can use any reporting tool on the top, Tableau, Looker, as well as notebooks like Jupyter, Zeppelin, etc., to access and analyze data. On the bottom, you have data lakes like S3, as well as a range of other data sources, NoSQL relational databases like MySQL, Postgres, streaming data sources like Kafka, caches like Redis, and real-time data sources like Pinot and Druid as well. So the question we get often is, what is Presto? Is it a database? How does it relate with Hadoop? So let me talk a little bit about this. Presto essentially is just the query engine. So if you think about more traditional database, it comes with compute and storage together, versus Presto, which is really just compute, and it runs on top of storage, which might be a database or a data lake. So it's really just a part of the database, which is the query engine. It comes out of the Hadoop ecosystem. It is the way it requires configuration management. It depends on the Hive metastore in that it is related to Hadoop. However, it is its own system. So you no longer need a zookeeper. You no longer need all the other components of Hadoop. If you query data lakes, then you need a Hive metastore or a catalog like AWS Glue, but you don't need any of the other components. And given that it is just a query engine, it's also different from a data warehouse, where the biggest advantage of Presto is you can query data in place. There's no need to move it, ingest it into yet another system or create another copy of it. So what makes Presto different from some of the other engines out there, like Spark? Spark was built to be a general purpose computational engine versus Presto, which is meant to be a SQL engine. It is highly scalable. It has a pluggable architecture with a range of connectors that you could use, and it's built for performance. It's built to be an in-memory engine with a pipelined architecture. Let's take a look at the scalable architecture. As I was mentioning earlier, we have two roles. We have the coordinator as well as the workers. The workers are connected to the data sources, and they operate on top of the data. They will have they can push down predicates, where clauses as an example, down to the data source, depending on the connector. In case of data lakes, the Hive connector is used, and predicates can get pushed down so that you can read little as less information or as less data as possible, pull it into the query engine to actually process it in memory. Uh, Presto is highly scalable. A very large number of workers are supported. And now with the advancement of multiple coordinators, it gets to be even more scalable. It's used at web scale at a large number of companies, big and small. Now, let's take a deeper look at the architecture. So if you look at the coordinator itself, it includes some of the typical components you would expect out of a database. You have the parser, compiler, analyzer. That's the optimizer. The optimizer decides that the planner is the optimizer when it decides on what plan is most efficient and should be executed depending on statistics and other information. The scheduler will then schedule the queries across the different workers. The data location API tells the scheduler where this data is actually located. And the metadata API gives the coordinator information about the tables, the columns, and the schema itself of the data lying underneath it. This might be via the Hive meta store, or it could be through a more traditional catalogs in a relational database, which are built in to the system itself. And at the bottom, the different connectors connect to all the range of different data sources. So let's talk a little bit more about the connector. Presto comes with about 30 different connectors. Here are some of the more popular ones. We often see MySQL, Postgres being the more traditional databases now. Many times you federate across not your primary engine, but your replicas. And so you can do replica reads on your MySQL or Postgres data. We see data warehouses like Redshift being queried across S3. Search engines like Elastic, NoSQL databases like Mongo or Cassandra, as well as streaming engines like Kafka. And all these plug into Presto. Presto allows for a query that can be joined across different data sources. So you can correlate data across different data sources. You just have to have the the schema name appropriately in the query itself. So a few different concepts. You have connectors, which allow you to connect different data sources into Presto, which is the query engine. The catalog contains schemas from different data sources. So for every data source that you connect to, you have to have a catalog.properties file. This file contains information about configurations of that data source. So it could be the URL information, it could be write properties, it could be credentials. A range of different configuration information is contained in the catalog properties file. And then the schema itself is the namespaces into, tables are organized into schemas. Tables themselves have columns and rows. And Presto is analyzes data using a columnar approach. And so here you see if you are working on HDFS or S3, the coordinator talks to the Hive metastore as an example, could be a Glue metastore as well. And then the splits are then assigned to different workers by the scheduler, which then goes and gets this information from the data lake underneath it. Presto allows for a different range of all different data types, different data formats to be queried. What we recommend oftentimes is ORC, Apache ORC or Parquet, formats, because those are the most efficient and most performant formats, also more compact. But you can query data that's in JSON, text CSV, and a range of other formats. The beauty of it is you don't have to ingest it into yet another system. It can be queried directly where it lives in the data source that it is located in. So why is Presto fast? We often get this question. When you compare Presto with Hive or some of the other more traditional query engines, depending on the generation, we see anywhere from Presto is 10 to 15 times faster in performance than some of these query engines. The primary reason is Presto is built as an in-memory engine. And so while you can spill to disk if the amount of information that you're processing is larger than the amount of memory available, most times, most deployments, users size their cluster to the amount of memory that is needed to perform the queries. And so given this, it's a very fast engine. It pulls the data that it needs. It's stream-based, and so it streams the data into memory as it's reading it, processes it, and then moves on to the next stage. It's also using a columnar execution that makes it very well suited to analytical queries. Now, a quick look at what a query life of a query is. In that is very similar to traditional databases. You have a explain plan. If you look at the explain, you'll see the different operators that are part of the plan. This is a simple plan for a select star from the orders table with a simple predicate. So you have the scan operator, which reads data from the orders table underneath. Filter is applied, and then the output is returned to the client. Slightly more involved query plan here. So you have a couple of projections. You have an aggregate, which is the sum, and then you have a left join on the line item table, which is on the order key. You also have a where clause and then a group by. And so the plan, you have the scan operator on the line item. You filter it out. You see a left join, which then and you have a scan on the orders table. This is then aggregated. The projections are pulled out, and the results are returned to the client. All right, so now let's talk a little bit about the use cases. So what I've covered so far is what Presto is, that it's a query engine, the architecture of Presto, why it's so fast. Let's talk about how people use it. What are the most popular use cases? So as I was mentioning, Presto began for interactive query, ad hoc query. And typically this is for dashboarding, as well as reporting use cases. Increasingly, it is for notebooks, for data science use cases, and also for federation across. So let's take a look at some of these use cases and what the stack might look like. So for the reporting and dashboarding, you might have a stack that looks like this. You have Tableau on the top, which is your BI tool. You use your standard JDBC driver. You connect to a Presto cluster, and maybe your data is in S3 as well as MySQL. For S3, you could use a Hive Metastore that maps the objects underneath to tables and columns. And you may have another catalog, which is MySQL, where you can perform a join across these different two data sources within Presto, and then return that information to your reporting tool on top. Range of reporting tools are supported. Another one here is Looker. And here you might have data just in S3, and you might be using a Glue Metastore. So this is, these are some of the typical stacks that you might see with Presto in the reporting and dashboarding use cases. Another popular use case is data science. You might have Jupyter notebooks. These are SQL notebooks where you might use Python and the Python SDK on top of Presto to then connect to the data lake or the relational data sources underneath it. Or you might use Zeppelin or a combination of different data sources, different notebooks on the top, which then connect with Presto and give you access to a range of data sources underneath. Federation is also a very popular use case. Of course, you could use it with any BI tool or notebook on the top. And the power of federation is you can essentially correlate information that may live in different data sources. So a query can span across, and a join can be performed across the different data sources, as I have been mentioning earlier. Now, increasingly, over the last year or two, Presto has been used for transformation or cleansing workloads, batch workloads, longer running workloads. And here you might use tools like Apache Airflow on the top, which then runs a SQL query that might either perform an in-data lake transformation. Let's say you convert a CSV, a set of CSV files to Parquet, or you may perform, you may move data from one data source to another, and do a create table as, and select from another data source. So these are some of the examples of data engineering workloads that are now being run on Presto. And one of the use case, one of the technologies underneath is Presto on Spark. Presto can now be the layer on top of your Spark jobs and allow you to run more robust and reliable batch workloads. And Tim will talk a little bit about this later on. And then finally, you're seeing the lakehouse become more popular. And the lakehouse really isn't anything different from a data lake. What it means is that some of the capabilities of a warehouse are now being moved to the data lake. One of those is transactionality. And this is achieved using technologies and projects like Apache Hudi, Delta Lake, and others. And this is a layer that then sits on top of the data lake that you can query with Presto. And so this is architecture for the data lake house that is emerging, and we're starting to see this more as well. And then finally, a little bit about Ahana. I'm one of the co-founders of Ahana. It's the Presto company. We have a strong database and Presto experts that have founded the company. And the product at a core is a managed service for Presto. It comes with a SaaS control plane and a managed service backend, where we bring compute and Presto to your data in your own account in AWS. Single pane of glass allows you to manage multiple Presto clusters, fully integrated and cloud native. And with that, handing it over to you, Tim.
Thank you, Dipti. Next up, I'd like to talk to you about Presto's roadmap and what we've recently accomplished and the direction that we want to take Presto into the future. And it can be summed up simply as Presto for all. Presto works really well as an interactive query engine. It can unify various data sources in your warehouse and provide you with a consistent interface into the data. We want to make the experience effortless going into many other use cases. One such use case is reporting and dashboarding. We want Presto to be the default choice for dashboards and to effortlessly handle the volume and the query shapes that these tools send to Presto, including anywhere from something that's checked in on once a month to something that's shared with the whole company and has a very large amount of traffic. We want Presto to be the default tool for these types of use cases, including BI tools as well. Presto is already a great choice for interactive ad hoc analysis, and we want to make it even better and even more flexible and to handle any number of query shapes that are thrown at it. So we want to continue to improve our ad hoc analysis and make it a really great ad hoc engine. We want Presto to be able to efficiently serve data without having to without having to ETL it from your warehouse. So we want Presto to be able to handle high QPS or queries per second use cases, such as external, a query, external facing websites that might send a query for some data efficiently and with minimal ETL to other storage solutions. So we don't want to have to introduce the need for a new kind of storage solution. We want to use the existing tools in the warehouse to be able to serve these use cases. And finally, at the totally opposite end of the spectrum, we want Presto to be able to handle large workloads with ease. So this is currently challenging because Presto is an in-memory query engine But as you'll see later, we're working on ways to make this more flexible and to handle very large scale batch type of workloads without requiring a rewrite and without using different code that may have different semantics or different outcomes to the data. We want to use good old Presto for even these sort of like far end batch ETL types of use cases. And the most important thing is that we want to consolidate on the same language to do all of this with similar ETL and with a unified storage backend. So once again, the more tools you need to support various different use cases, the more complicated and expensive things get. So we want to avoid having to reach for a new tool to, let's say, serve a very popular dashboard or to serve data to, let's say, a website. We want to use Presto for a variety of different purposes and consolidate on a single tool that has similar support characteristics across all these use cases and is familiar to the people supporting it. So like we don't want you to have to learn a new tool and get used to its quirks and kinks for you to accomplish the things that you need to accomplish. So the big question is then, having stated all these different use cases that we want to target, is what are we doing to help scale to fit these different workloads and to support them really well so that, they are the default choice that you reach out to. And the most obvious thing is we're adding more connectors. Connectors are a seamless way to get Presto to plug into other data sources and open up these new use cases. Connectors are a very natural choice to plug into other data sources so that you can use good old Presto to access the data that are found in those sources. So some examples of new connectors are we've added support for Druid and Oracle connectors, and down the pipe we also have support for Iceberg, which is a very important connector to solve the metadata scalability challenge that large warehouses have, support for Prometheus data sets, and then also integration with Google BigQuery. But connectors aren't the whole story. Connectors solve very particular problems with particular data sets, but connectors alone won't help us accomplish all of the goals that we set out earlier. So there's a lot more that we have to do. And another thing that we have to do to make Presto the tool of choice is better handle workloads that don't fit entirely within memory, as Presto is an in-memory query engine. So we've put in a lot of work on adding more operators to participate in spill to disk, which is a way to enable queries to use more memory and bypass the local memory requirements that may exist on the worker. But in addition to adding more operator support, which opens up various different scalability challenges within various different query shapes, we've added the ability to configure where the spilling output can go. So in case you have an external storage service that you would like to use for like these sorts of temporary data sets, or if you would like to use something other than local disk, you have the flexibility to do that. And we have also added more strategies to configure exactly how spilling occurs when it's needed to occur, which will improve the reliability of the Presto cluster. So next we have, in addition to workloads that don't fit in memory, we also want to target workloads that run for many hours. And this is challenging because as Presto doesn't have built-in fault tolerance, there ends up being a correlation with how long a Presto query runs with its likely, like probability of failure. So opening up Presto as a good default choice for queries that run for many hours is challenging because there's lots of implications on failure recovery that need to be handled. And the ultimate goal here is to prevent the need from rewriting the query in a different engine that may have different semantics or different function support or various other differences that make it difficult to reason about and introduce overhead for the person who's migrating it from Presto into suppose Spark SQL. And that's why Presto has migrated its query engine into a library that can be run on Spark. So by leveraging Spark's resource management and checkpointing features, we can enjoy the benefits of disaggregated shuffle and recoverability that Spark provides without having to rewrite the entire query from Presto Classic. So using the exact same query, we can actually execute the Presto query on Spark and use the same Presto operators, the same, basically everything is the same except for the shuffle and recoverability features. So an example is a query that used to run just fine on the classic streaming model of Presto, but now suddenly hits memory limits or takes much longer to complete because there's an influx of data, and because it takes longer to complete, it's more likely to fail. Such queries can now be reliably executed on Spark without having to rewrite the entire query. And so that's the story that we have for queries that run on many hours and queries that don't fit in memory. But we also have at the totally opposite end of the spectrum, we have this desire to handle use cases that may be very short, serve data that could be externally facing or could, for various reasons, have very high QPS. And something that may be customer driven. We want to use the same query engine for this spectrum of queries as well. And to accomplish this, we've been working on reducing the query latency within Presto to be a more natural tool to support these types of queries. And the biggest thing that we've done is introduced basically a project known as RaptorX, which is intelligent tiered caching that gives you performance as if you have co-located your compute with your storage, except it gives you disaggregated storage. So like, let's say S3 or some cloud providers where you're putting your storage, using caching, you can get this co-located like performance using purely disaggregated storage. So this opens up a lot of flexibility in terms of being able to scale your storage independently from compute, to leverage your existing cloud storage solutions and not have to do any sort of special ETL in order to get this improved performance. Using your existing cloud storage provider, we now have a caching layer that works on top of it that can vastly increase the performance. And in addition to RaptorX with caching, we also have materialized view support, which is being worked on, which will allow you to create, using standard SQL functionality, create a pre-materialized view that'll allow you to very quickly query roll-up tables without having to either repeatedly calculate all these metric roll-ups or without having to create a pipeline to create a derived table to pre-compute your metric rollups. You can now use standard Presto SQL, or you'll soon be able to use standard Presto SQL to create an external materialized view and just point your query to the materialized view. So in addition to adding support and sort of like increasing the breadth of support that we think that Presto can offer, we also are working to make Presto by default more efficient, more reliable, and more scalable and extensible. So we want to also improve sort of like the core Presto code across all use cases. And just improve it across really all aspects, but in particular reliability, efficiency, and extensibility. So in terms of reliability, we are adding support for disaggregated coordinators, which means that you can spin up multiple coordinators to serve your queries, multiple coordinators to serve as a source of redundancy for the coordinators, so that in case for whatever reason a coordinator is lost or needs to go down for maintenance, you don't lose access to all of your compute. You have the ability to swap it with a different process or to spin another one up very flexibly without having to lose all the running queries that were sitting in front of that coordinator. In addition to adding multi-coordinator support, we're working on adding the ability to effectively bin pack where tasks are scheduled, so that we increase the memory utilization and CPU of the running tasks on the workers. So this has interesting consequences, because the current scheduling model, which schedules work randomly, tends to lead to hotspots and to lead to inefficient memory utilization. By efficiently scheduling work based on how the current workers are loaded in terms of CPU and memory, we can actually increase throughput and increase reliability in terms of memory limits by just sort of like taking that into account during scheduling. And a simple but effective one is we've recently added the ability to transparently retry a query in case it fails. So suppose a query fails due to node failure, swapping a machine, or let's say a network partition. Presto can transparently retry this query, provided it's within certain reasonable time limits and reasonable other limits. Presto can now transparently retry the query, so that it doesn't really require any intervention from the person who submitted the query. In addition to reliability, we're also focused very much on efficiency. And the big one is native execution. So we're working right now to migrate our entire eval engine into a native C++ worker, so that we have better control over memory utilization versus the standard Java worker, and better control over the instructions used. So for example, vectorized instructions or SIMD instructions, so that we have, in certain circumstances, orders of magnitude type of performance improvements just by using sort of like closer to the hardware types of instructions. So this is in progress, but we're also very excited about its introduction in the coming months. In addition to native execution, we also have, we're also working on integrating existing ARIA improvements into Parquet. So we added a set of efficiency improvements called ARIA, which adds expression pushdown all the way into the scan. We added this to this ability to ORC last year. We're now working on integrating the same work into Parquet files, so that Parquet files enjoy the same benefit. And in addition to reliability and efficiency, we're also working on making sure that Presto is very highly extensible. So one way of doing this is we've added support for SQL functions, so that if you have a complex, let's say a complex mathematical expression or some sort of complex function, you can better encapsulate it inside a function, and you can share it with others in your team by simply adding a SQL function to encapsulate that expression. And finally, we've also added the ability to query an external UDS server for function execution, so that suppose you have, let's say, some piece of code that's written in only one language and it's difficult to port into, let's say, Java, you can, or standard SQL, you can query an external UDS server to execute that function, or you can, if you have a desire to separate out a particularly heavy function into a different compute pool, you can point it to a cluster of thrift servers which can serve this function. So we've added the support for having functions point to external external servers, which may be written in a different language and may maybe not co-located or put in a different location. So that's it for my update. I just wanted to thank you for attending, and I'll be excited to see you at the upcoming sessions at the Presto track.